In this video, I'm going to solve two examples that help you to practice the relationship between F, the electrostatic force, and electric field and the charge of particle. You know, the relationship between electric force and the electrostatic field and the charge is F equals to EQ. In the first example, we would like to calculate the force exerts to a 2 microcoulomb charge. So first I extract the data Q1, or the only Q that we have here. So Q equals to 2 microcoulomb. Don't forget to convert it to coulomb. 10 to the power minus 6 coulomb. You know that micro is 10 to the power minus 6 charge that is located in an electric field with a magnitude of 4 Newton per coulomb. So we have the magnitude of electric field that is 4 Newton per coulomb. And we are looking for force. How much is that force? So force is a vector, and you know, as you watched in my previous videos, for calculating a vector, you have to calculate both magnitude and direction. Otherwise, your solution is not complete. So which formula I'm going to use? It is F equals to E, electric field, times Q. So first of all, I'm trying to calculate the magnitude. So force F, when I'm writing like that, it means the magnitude of F, the magnitude of E, times charge Q. Q or charge is the scalar, okay? So I can write 4 times 2 times 10 to the power negative 6 coulomb. That is 8 times 10 to the power negative 6 Newton. Okay, because that is Newton. The unit for 4 is Newton per coulomb. You know, coulomb and coulomb cancel out, so dimensionally that would be correct. This is the answer for this question. In which direction it will move? Because it is a positive charge, positive 2 microcoulomb, you know that positive charges will move along the direction of electric field. So it is supposed to move toward right, like this. Next example. In the next example, we have a negatively charged particle that is suspended in an uniform electric field. This word uniform electric field, I would like to explain a little bit about this. When we say uniform electric field, that is an electric field that its lines are parallel, and you know, the density of lines are the same everywhere in the space. So one way to create the uniform electric field is to locate two metallic plates that they are charged with opposite charges, positive and negative, like what you see here. That is the cross-section image of two plates of two charged plates with the positive and negative charges. Then in between them, you can have a very fine parallel lines electric fields. That the density of electric fields, I mean the number of lines per unit of area, is the same here. So, but you know, at the edge of these plates, the electric field lines will bend like this, and we cannot say that the electric field in these areas are uniform because they are not parallel, the lines are not parallel, and as you see, the density is not uniform. If I consider this thing here, the lines are more close compared to this. So the best way to create a uniform electric field is to put two parallel plates of plates that they are charged. Okay, then what information I have? This particle has a mass of 2 grams. I have to convert it to kilogram. 2 times 10 to the power negative 3 kilogram. You know that 1 gram is 1,000 thousandths of 1 kilogram. And its charge is 4 microcoulomb. 4 microcoulomb. I'm pretty sure that you never forget to convert this to 10 to the power minus 6 coulomb, because we are working in the SI units, so standard international units. Calculate the magnitude of electric field. We are looking for electric field. How much is direction is determined? It is from top to bottom. Okay, so that's like dynamic question, because we are talking about force. G is the gravitational acceleration, 9.81. If I draw the free body diagram for this object, there is a gravity force downward. That is mass times gravity, correct? This is weight. And the other force is upward, actually. That is the force of electric field. Because you know, the negatively charged particle likes to move in opposite direction. You remember in the previous videos, it likes to move upward. Okay, from negative sides it is repelled, and from a positive side it is attracted. So we can say this is the F electrostatic. But it says it is suspended. When I say it is suspended, it means these two forces are canceling out each other. So I can write that two forces that I have, F of gravity, force of gravity, that is mg, and electrostatic force, that is eq, correct? And as it is suspended, fg is equals to fe. Let's plug the numbers. mg equals to eq. And if I isolate for E by dividing both sides to Q, I have mg over Q. Let's plug the numbers. Mass is 2 times 10 to the power negative 3 kilogram. Gravity is 9.81 meter per square second. And Q is just 4 times 10 to the power negative 6. If I do the calculations, this 2 and this 4 can be cancelled out, and I will have just a 2 here. So there's 9.81 divided by 2. This is the numbers, 4.9. So it gives me 4.9 times 10 to the power negative 3. I can bring 10 to the power negative 6 to numerator, to the top, plus 6, and convert negative to positive exponent. And you know, when the bases are the same, you just need to add these two exponents. 6 plus minus 3, or 6 minus 3, is 10 to the power 3. And the unit is Newton per coulomb, the unit of electric field. This is the answer for this question. You may face this problem in your examinations or whatever. the teachers may convert this negative to positive and just flip the side of electric field. The process is quite the same, and that's it. I hope you learned it. Don't forget to send me your feedbacks, write a comment, like it, dislike it, then I will know you enjoyed this or not.